Swayam Prabha. Digital India. Educated India.
Okay, so Chrome browser, which most of us are using, would be running as a multi-process.
Yes, sir. Its tab will be as a multiple processes.
Yes, and it's not even multi-thread, it's multi-process. Keep that in mind. But to make sure that the user sees it as in one application, there is a controlling process, right? So there is a browser, which is the process manager for the whole user interface. It also coordinates how we talk to disk over the network and so forth. Each of the tab is actually a different process, which is rendering the tab to the user. And the reason we are doing this is because then each tab can have an isolation or sandbox or security, so that a compromise of one tab is not leading to a compromise of another tab, or for that matter, the whole system. Right? Now, in this case, decoding HTML content, I'm just giving an example, could be a library which is available, and this library may be shared for each of these tabs, in which case a single page is used across multiple processes. Does it make sense?
Yes, sir.
This is purely for code being executed. How about data, which is both read and written? There will be different pages for that as well. In which case, each process will have a unique set of modifiable data, because process one modifying its variable should not be visible to process 2. That is not the same case with threads, as Abhijat sir discussed in the first half. Threads share their global variables, but processes do not. Did it get a bit clearer for you, or is still having some confusion there?
Yes, sir. I think I confused between the processes and threads actually.
Okay, yeah, that is a possibility. And today, as we do the exercises, we will get better at it through hands-on experience.
Yes. So in this context, let's suppose we have these tabs and we have these different processes. So this browser will be available and all these processes will be available in our memory. So now the working of operating system is what is to divide it into pages and then put it into the memory and get the memory available memory for it.
Correct.
So
It's just the memory
we
management
have
part. Yes.
yes. So we have only one perfect memory, right? One primary memory. So everything will be decoded in that decoded in that primary memory, and pages will have some memory as allocated by our OS. Now,
This
as we
primary
have
is
this
more like
memory,
what you mean physical memory. Yes.
yes, sir. So now, when we have now two cores, so these processes, I guess, like if we have the first tab, it can run on the first processor, and the second tab can run on the second processor, right?
Yes, that is the idea.
So it's because we have those tabs independent of each other. They are not interlinked. That's why we are doing it.
No, even if they're interlinked, and that is where I said an example we will cover shortly, where multiple threads of the same process can also be distributed across cores. But then in that case, the onus lies on the developer of the application to ensure consistency is there.
Okay, so he needs to manage between both threads, like which line should go first and it should not go. Like
Out of order
we don't have
execution
the
should not
control
happen.
hazards and data hazards as
Correct.
we should have. Okay, sir. So these all should be controlled by the main operating system and this
No, no. So
coding
again,
part of the
I would
browser.
step back and say, if you're going multi-threaded, as an
Yes.
application developer, we have to take more control. If we are as multiple processes, independent processes, operating system helps us get that segregation as far as safety and other things are concerned.
Okay, sir. Okay, sir. Yes. Yes, sir. Got it. Got it, sir. Yes. Thank you, sir.
Yeah, because threading, at least the threading on Linux and Unix, which is POSIX thread, is more through a library, enabled via a library. That's why. Okay, so let us
Okay.
start with the afternoon session, and we are primarily going to talk about inter-process communication. Now, just taking this example of Chrome browser, suppose one of the tabs we have opened is a WhatsApp or an email, right? A new email comes on, depending on the platform on which you are working, there can be a notification that pops up to you, right? Or a WhatsApp message comes, a notification pops up. On my machine right now, I have disabled it, but if I enable it and if somebody messages, it pops up. Have you experienced it? So what I'm
Yes, sir.
saying, that osbooks.com could be web.whatsapp.com or web.telegram.org or whatever. So if there is a new message being coming, on the bottom right, there would be a pop-up that will happen automatically.
Yes, sir.
Right? The fact that the message came would be only known to this process that is helping us render this specific tab. Then through the browser manager process, which is another process architected as part of this browsing application, it tells the operating system that I want to notify it. And then between Windows 10 to Windows XP, there could be different ways of that notification coming back to us. So this is how they have architected a particular application. A master process which is helping coordinate others, and lot of processes, one for each tab. Furthermore, because the browser has extensions, these extensions can be labeled as plugins. They become separate processes themselves, so that a misbehaving plugin is not impacting a particular rendering session or the whole browser. Does it make sense?
Yes, sir.
So single application with multiple processes also needs a good collaboration across them to give a very good user experience. And that is the underlying principle for inter-process communication. If they do not talk to each other, how can they effectively talk to the end user? Again, this is one way of looking at it. There are other ways of also looking at how inter-process communication helps us do things in a better manner. So processes within a system may be completely independent or they may be cooperating in nature. What can be a completely independent process? Let us say a web browser coming from Google may not care about Microsoft Office tools on my PC. Then they are completely independent. And this used to happen 5 years back. Now today, with Office tools itself becoming Office 365 or similar, they have started to become more interdependent so that they can give a better user experience optimized for a network connected computer and so on. Cooperating processes can affect or be affected by other processes, including how they share their data. And this is the part we will be focusing on for today afternoon. When we have to cooperate with each other across processes, we can have different paradigms. Client server is what we typically know with web browsers. Server is giving content, client is showing it to us. We may also have publisher, subscriber, minor difference to notifications and so forth. If you go to mobile perspective, you have intents and activities and other patterns for communication. But in essence, many of these things are primarily about sharing data or sharing state and so on. Now, either we are sharing information or we are trying to go and do things in parallel so that we can be faster. Or it could be for modularity. Remember the browser experience case, the plugins have to be modular. Having them as a separate process enables more modularity. It could be just about convenience. If we can have a different process do some things, it's easier for us to keep calling that process to keep on doing it in a repetitive mode, for example. And because these cooperating processes need to talk to each other, so inter-process communication comes into play. Two primary models have been there at least for the last 50 odd years since Unix existed. Shared memory and message passing interface. Additionally, there are two helping blocks that help us sort of set up inter-process communication. Signals, which I will not spend as much time today, but if you're interested, you can go ahead and look at it. And mutex or semaphores, very closely related, but again, we are not spending time with them today. We will primarily look at shared memory, message passing, and then later with respect to threads, we will look at global variables, and that is where some critical sections and other things we start getting towards. Any questions so far? Okay, so let us look at the shared memory versus message passing. Again, this is not the page oriented view, but similar view is what I am borrowing here. Process A and process B both will have access to the same memory segment. Then across processes, we are sharing things in memory. This is the basic principle of shared memory. The moment we have shared memory, almost always both can read or write. Again, how we end up sharing, we can say that we only want to read or we only want to write. Those rules can be put in. But it's not that process A can depend on the fact that all other processes will only read. It may be that another process will also write. So there could be multiple writers problem, and all those things can also happen. So simultaneous updates and similar issues will be a challenge there. On the other hand, and by the way, I'm showing only two entities, but shared memories can be for more than two entities also. We will demonstrate through example shortly. Message passing, on the other hand, is sort of like setting up a pipe. And there would be one end through which we insert messages, and there would be another end, if you're doing a FIFO approach, through which we take the messages out. So there will be a message queue maintained with some level of sequence numbering and other things. This is done by the kernel. So this is very important to know, that message passing is enabled by the kernel. Shared memory, the setup is through the kernel, but the coordination has to be done by the processes. Is that coming out clearly? To allocate the same set of memory pages across two processes, because shared memory is precisely that, we will need to do system calls with the kernel. But once it is set up, who is writing, when they are writing, how they are synchronizing has to be the logic of the processes. On the other hand, when we are using message queue, process A will send and process B can receive, or both process A and process B can send and receive, but send and receive themselves are system calls, which means kernel is much more in control for the message flow. So quickly, let us look at producer-consumer problem. This most of you would be exposed to, but we will recap all the same. So there is, and for simplicity, we will just say one producer, one consumer, but in real life applications, we will see that there can be multiple producers and multiple consumers, one or more in both categories. So producers will produce information that is consumed by the consuming process. When we are implementing it, it can be done in two manners. One is unbounded buffer. So sort of it says there is no practical limit on size of the buffer. Though in reality, when we implement it, there would be some limitations. But if we have an idealistic solution, producer will never have to wait. They keep on sending messages. Consumer will keep receiving it, and if there is nothing available to consume, they will wait. More practical implementations will have bounded buffers. They can only buffer certain amount. So if the queues are getting filled up, if there are no more resources available, producer will have to wait for consumers to read and clear up the buffers so that they can be recycled. So in this case, if consumer is slow, producer will finally have to wait. In this case, producer never waits. But this is more idealistic, and many a times old messages may be removed to clean up buffers if needed. Again, that will be an application layer logic. So with respect to shared memory, what happens is, with the help of our kernel, we will allocate space, and then another process can allocate the same set of space and map it within its virtual memory map. The coordination and communication will be under the control of user processes, not the operating system. Very crucial to understand this. Race condition and memory corruption can happen if we do not take care. And major issue here is to provide mechanism which will allow user access to synchronize their actions when they are being accessed from the shared memory. Again, the semaphore and the other part that I've skipped from the textbook perspective, they're covered in chapter 6 and 7. Some of you who are interested can go further and explore that. So let us say that there is a data structure that we want to have it in shared memory. We will have some instances of it. In this particular case, instance count is set to 10. And then when the producer is producing and consumer is consuming, generally speaking, we should have only 9 elements there. Adding 10th element will need the memory to be properly accommodated, because then the insert and the tail would sort of start getting wrapped around each other. So look at the producer's logic. Producer is doing something here to produce that item. Let us say that this message is getting populated with some real world inputs. And then we are saying at the input pointer +1, percentage buffer size, which is in this case 10, is not equal to the output pointer, where the consumer is going to read the next value. We should not insert, we should wait for it to be read. Basically, we are trying to make sure that there is always one buffer that is not in use, and that can be sort of our isolation boundary across a circular buffer. This modulo operator here is making sure the buffering is happening in a circular manner. If the consumer has read things, this condition will not be true. So at the in location, we will put the next item that we have produced and increment the value of in, again modulo buffer size, to make this a circular implementation across a linear array. Does this make sense? Any doubts around how this modulo operator is helping us have a circular list of buffers on a linear memory? We have not worried about how the memory is set up yet. Don't worry on that part. As far as consumer is concerned, if there is nothing produced, in this which case in and out are the same, it cannot progress. It may just go back to sleep or whatever. Otherwise, if there is a difference, it means there is something that has been produced. We will read from the out location and shift, increment the out by 1 modulo the buffer size. This again is, in both the cases, we keep on incrementing by 1 modulo the buffer size, and that's how we are, modulo is making us go into the circular implementation. So once we have read this thing next consume, we can process it here. Once we have done processing, we will come back in the loop. So this is a typical coordination between producer consumer using shared memory. We have not covered yet how the shared memory is being set up. We have also not covered yet how do we make sure increment of out and increment of in is not impacting these condition checks. Can anybody try to discuss why this condition check may have an issue? Or for that matter, even this condition check. Remember, this in and out are variables that have to be shared across these processes, or they have to be sort of coordinated across these processes. So they themselves are global variables shared between the processes. Does it make sense? If the reference to in for the consumer is not in sync with the reference for the producer, will that be a problem? The shared memory will work only when both producers and consumers have a common understanding of in and out values. Otherwise, it will not work. So that is again something that has to be synchronized. Sorry about the background noise. I hope that is not disturbing too much. So let us say that the producer is going to fill out all the buffers at one go in a very quick manner. There can be a counter that starts off at 0 and incremented by the producer. And similarly, the counter is decremented by the consumer after it has consumed it from the buffer, which means this counter as a variable is shared across both these producer and consumer. So in this case, till we hit the buffer size, we don't have a problem, we can produce. We increment the input value and also increment the counter. In case of consumer, now the counter is the only thing that we are sharing with the other application, with the producer, and we are looking at decrementing the counter after we have consumed it. So out can keep on changing here and in can keep on changing here. We have decoupled from two variables needed together to just one variable needed to be synchronized between producer and consumer. Now, in and out are more local to the context of producer and consumer. And as long as we only have one producer and one consumer, we do not have to worry about synchronizing them. The moment we have more than one producer, all producers will have to worry about synchronizing the in value. And similarly, all consumers have to worry about synchronizing the out value. Now let us see how the race condition comes into play across these processes, even if they are mapping to the memory. Remember, to increment, we read the value from RAM into a register, then increment the value in the register, and finally store the value from register to the memory. We are not going to go into cache and other things. If there is L2 or L1 cache, that adds to the confusion further. So this is something we have covered in the previous days. But even if we keep the caching aside, just a simple increment or a decrement is a 3 instruction process. And for simplicity, even if we are running with only one CPU core, we may have conditions like this. If we are running with more than one CPU core, each of them executing in parallel, we can have even bigger race conditions than what we are capturing here. So the first time we have got S0 with producer and S1 with producer executing. These two instructions get done, and then a context switch happens. Let us say that the timer runs out. For S2 and S3, we are executing these two instructions. Then we come back and execute the third instruction of the first set, and then the third instructions of the second set. So what do we end up with? This race condition actually ends up with starting with a value of 5, moving to 6. The other guy is moving from 5 to 4. And finally, instead of storing 6, we are storing 4. Right? So can you understand how this race condition has happened? Let's keep it interactive, or I will get into a monologue and this will not help anybody. So this, what it really means is, this is the critical section that we have to protect, and this is another critical section we have to protect. And as long as somebody enters into one critical section, nobody else should be able to enter there. So this is when we are going with counter-based approach. If we were using two variables in which the producer was incrementing one and consumer was incrementing the other variable, we were not having a race condition because updates were happening only in one of the process for one of the variables. They were not being simultaneously updated by both the processes. And hence, in the first approach where there is an in incremented and out incremented, and both these variables are being shared together, which meant we could only use n-1 entries, we did not have that race condition. So again, a simple change of rather than sharing two variables, sharing only one variable and trying to use all n spaces opens up a possibility of race condition, even if we have only one producer and one consumer. Now going back to this example, if there were multiple producers and multiple consumers, both the approaches will have challenges. With me so far? Okay, great. On the other hand, as I had mentioned in the very beginning, with the message passing, we do not have such race conditions because the kernel or the privileged space is helping us coordinate the messages. There will be a send and a receive, and the message size can be fixed or variable, depends on the way we are instantiating the message queues. So if processes P and Q wish to communicate, they need to establish a link between them and then exchange the messages using send and receive for those links. A good practice is always to have unidirectional links, in the sense you should not be reading from the same interface on which you are writing. Again, through examples of Unix pipe, we will look at it after I'm done with the slides. So exchanging the messages is via the calls to send and receive. Very similar calls will again get covered when you are looking at networks and communication between systems. So send to, receive from, and similar constructs exist with respect to socket-based communication. Now, purely on a single system, we're talking of a single computer right now. This communication link across processes, how do we establish? Can a link be associated with two or more than two processes? Remember, many times we want to coordinate as one-on-one, but there will be scenarios where we want to multicast or broadcast. Everybody has to be notified that an event has happened. So can we support such scenarios? Again, these are some of the implementation aspects. Unix takes a different approach. Linux has taken a slightly different approach. And then Windows and others will have, again, its own set of approaches there. How many links can we have between every pair of communicating processes? Will the kernel restrict or enable multiple links to be established? In what aspects are the capacity of the links going to be constrained? Will we have an unbounded buffer? Will it be bounded buffer, and so forth? And then what is the maximum size of message a link can accommodate? And finally, the link itself, is it unidirectional or bidirectional? The textbook, the way they have covered, they have even got to socket communication. We will not go there today. So we'll quickly look at just the first part, the shared memory and hardware bus sort of approach, not the network approach. So typical communication link can have buffers in kernel space. When we are saying this shared memory, through libraries, we can do it with shared memories, but it can also be kernel space memory that we are talking of. There can be hardware bus elements through which we can do it. Obviously, over the network is socket communication. And then in logical manner, we may have it as direct or indirect, synchronous or asynchronous. and then automatic or explicit buffering. Will the buffering happen by default, or will the buffer levels be set by the application before they establish the link and so on? So these are some of the implementation specific aspects. So generally speaking, when a message is being sent, we have to tell which is the entity that will be receiving the message. Now, in this case, we are saying sending message to process P. How do we know the details of process P itself is to be sort of discovered or decided in advance. Similarly, when we receive the message, there are two ways of looking at it. One is receive the next message and tell us who the message has come from, or receive the next message from a specific user. When we have a direct connection, let us take the analogy of a physical world where we can directly talk through letters or through dedicated channels like direct hotline based phone calls and so forth, right? When I pick a specific phone, let us say the Prime Minister of India has a hotline with Premier of China. Depending on the phone they pick up, they know who will be the person at the other end. So it's very explicit. The links are established automatically. They are exactly between one pair of communicating processes, in this case, Prime Minister of India and Premier of China. And between each pair, there is exactly one link. And most of the cases, this will be a bidirectional link to allow communication flow to be seamless. Now, this is the idealistic real world sort of scenario where you're willing to spend so much effort and resources to maintain that link between two very important entities. In virtual space, we tend to utilize systems by sharing resources, and we may not explicitly carve out such direct communication. So this is where the messages are directed and received via mailboxes, also referred to as ports. This is akin to saying that the postman or the delivery mechanism would collect things together, carry things together, and try to have better utilization. They're not going to carry each and every message, rather they will combine them and then distribute them. When they're distributing it, each mailbox has a unique ID, and processes can communicate only if they share a mailbox. So my office door number is, let us say, 305. My mailbox number may also be 305, in which case everybody will know my office number is my mailbox number, and they can reach to me using that with the address of my institute. Now, if somebody doesn't know my mailbox number, they cannot talk to me, right? So again, that prior knowledge is needed. So that is where for communication link to be established, we need to know the common mailbox through which we are exchanging the messages. A link may be associated with many processes, which means many people can drop messages in the mailbox and many people can pick messages. And the link may be unidirectional or bidirectional. Another behavior of the mailbox could be that, and this especially goes into the paradigm of notification, when you're looking at notifications and so forth. While in physical world, a letter that is picked once cannot be taken by anybody else. In virtual world, for each of the entity that needs to be notified, the message can be copied and given to them. So again, there can be more value addition that can get done with respect to communication there. One-to-many communication, we can create multiple copies and give it to them. So when we are looking at indirect communication, we have to sort of have a way of creating a mailbox or a port. Then there has to be interfaces to send and receive. And finally, we may want to tear it down, because if you're not using it, better not keep the resources pending with the kernel. It's like garbage collection will only trigger in if your mailbox is deleted. So in this case, rather than having to send directly to the other entity, we will be sending the message to the mailbox and we will be receiving the message via a mailbox, and the mailbox is our buffer space. Now, with respect to sharing the message, P1, P2, P3 are sharing a mailbox. P1 is the sender or the producer. P2 and P3 are consumer. Now when P1 sends, who would get the message? That will depend on the business logic or the application logic that we want to build into the mailbox system. So can we say that at most two processes can access the mailbox at a time and they have to be of a different approach? One has to be producer, one has to be consumer, maybe. Do we want to restrict that a message can only be executed or received by one entity? That can be a logic that we can implement. Or do we want the system to arbitrarily select the receiver and then the sender is notified who the receiver was? This makes more sense when the sender is expecting some activity to be performed, some service to be performed, but does not care who the server is. In which case it does a anycast, sort of anybody who can do this, please do it for me. And once somebody is assigned to do the work, the sender is notified as to who has done the work. Now, when we are looking at such message passing approaches, again, we will have some level of synchronization to take care of, or some level of blocking, unblocking to come into play. More so because resources will be limited. So one category is blocking synchronous communication. Sender makes a call. Till somebody receives it or acknowledges the receipt, the call will not complete, which means it's a synchronous blocking call. So sender is sending it and getting blocked. Receiver is blocked until some sender has sent a message. There can be asynchronous non-blocking approach also. Sender sends the message and continues to do other work. Similarly, receiver checks, is there a message pending for me? If it is, it will act on it. If there is no message pending, it continues to do some other work. It's also possible that sender may be synchronous, receiver may be asynchronous, or vice versa. So those implementations also exist. When we are looking at producer consumer using message passing, as far as producer is concerned, it will produce the item and send it. Consumer is concerned, it will receive the item and then process it. Now, compared to the shared memory, this logic looks very simple. The primary reason being both send and receive are system calls, and the operating system is taking care of the complexity for us. In this case, the buffering itself will depend. When we are setting up the message queue, we will decide how much buffering or what type of buffering we want. Zero capacity, which means both are synchronous sort of. No messages are queued in the link. Sender must wait for receiver and then only the message gets sent. There can be a bounded capacity or an unbounded capacity, in which case the sender never waits. So coming specifically to the shared memory part, shortly I'm going to go into a break. When I come back, we will look at examples of this code. So we will use both shared memory and pipes. We will not be using message queues, but we will use pipes for communication, which is a message passing interface built with parent-child relationship. That is what pipes are about. So shared memory, we will have to create it. Some entity has to create it and take permissions to both read, write, or just read or just write. Those things can vary. And then when it's created, there would be more file level permissions of read and write here. It can also be read, write, execute, and other things. It can be used to open something that is already created. Basically, there is this flag. If it is not existing, it will create it. Otherwise, it will just open to existing segment. So first thing is system open as a library call, which gets invoked as a system call finally, and then mapping the memory to a specific size, which is f truncate. In this case, 4 kilobytes of buffer is what we are mapping. So after we truncate, we will use a map so that this shared memory gets visible in our virtual memory of the process. Once it is mapped, we will be using mmap to further, sorry, we will be using just memory access, simple memory access to do a read and write from these locations. A quick look at the code that we will be running post break. Some standard includes for shared memory, a size of buffers, then a name through which the shared memory will get created. This has to map across the producer and consumer. And then messages that we may pass. This is just some housekeeping code there. Then the shared memory itself will be created as a file descriptor that will get memory mapped. So there is a file descriptor for that. And finally, once we map it to memory, there will be a pointer in memory. This piece of code I had already covered in the previous slide. Basically, with the name of OS, we are creating a shared memory resource. The kernel returns us a file descriptor with access of anybody can read and write. So this is 666. Then we tell the kernel that, okay, the size that we are looking at with respect to this file descriptor and shared memory is 4 kilobytes. And finally, we do the memory map. Once it is mapped, we can directly write to this location whatever we want to write. So in this case, message 0 followed by message 1 is what we write. And since we are appending, remember we are doing memory operations, so the pointer values are also getting adjusted. The producer is only producing one element and exiting. If it wanted to produce more elements, there could be possibly, okay, sorry, two elements in this case, message 0 and message 1. Now, interestingly, as we go further, we will notice that null termination of messages and all is something that as an application, we are saying message 0 terminates with null and similarly message 1 terminates with null. Similarly, for the consumer, initial part is very similar, but rather than creating, we will just be opening the same created memory with read only. We will map the memory space. Then we will read from the memory and print it. And finally, for garbage collector to come in and clean it up, we will have SHM unlink. Now, if we do not unlink, what it means is the shared memory stays with the kernel, and we can run another consumer which may be able to read the same content again without knowing that it has been consumed. So that there has to be some, this link and unlink is helping us do a little bit of garbage collection. The other aspect was we have printed two messages, hello and world, but we are reading only one message. So what do you think would have happened because of this? Do you think we will be able to get the whole message? Will we get partial message? What really will happen? So I will ask you to focus only on this line of read here. And these 4 lines of the producer part here. Message 0 and 1 are defined out here. Any comments? Okay, so let me now flip over and run this code for you. Okay, what I have done is I have already shared the link from where this operating systems concepts as a virtual machine instance is being created and run within VirtualBox. For ease of demo, I am not directly showing you the output in the VirtualBox, though it exists here. I am going to go through a PuTTY terminal, which is actually doing an SSH to the virtual machine and has a better display capability for you to understand. And remember, Abhijat sir covered the linking and execution part in the morning. So the actual files are available under course for operating system concepts 10th edition. I'm primarily focusing on chapter 3 for the demos today. And for the summer school, I have extracted 3 files from there: a shared memory, POSIX, producer consumer, Unix pipe. And then for bakery algorithm, we will discuss shortly. That is the 4th file out here. For compilation and linking, I am relying on makefile. At your comfort, you can use other approaches as well. But basically, it's a simple way of converting the C code to the executable through some proper grammar. And linking of libraries, setting the debug levels are also enabled here. For bakery algorithm, because I will be using POSIX threads, so I will be linking against that. Quickly running you through the code of shared memory. Let me go in VI, that is better. User, this is the same code that I have shown you. Okay. Producer will look at writing as well. So when we are doing memory map, we are writing. When we are creating, we are having both read writes. And then rather than 2 messages, we are sending 3 messages. What are the 3 messages? Studying operating systems is fun. There is a space at the end for all of them. Please stop me if I'm going too fast. As far as consumer is concerned, exactly the same code as before. We are just doing one printf. So let us first run shared memory producer. There is a sleep that I've added that is not as important. Shared memory consumer. So you will notice consumer runs and prints the whole thing as a single message. Studying operating system is fun. While the producer sent 3 different messages, consumer could not differentiate because there was a logical issue in our implementation. Can anybody help identify the logical issue? Generally speaking, when we are looking at sharing messages through memory, we cannot directly go with message. Typical approaches say that messages should follow paradigms like type of message or tag for the message, length of message, and value of message. TLV in short. Type or tag, length, and value. Only in that case, we will have a better coordination between producer or consumer. Other approach could have been to actually have the variables of how many messages we have produced, where is the head, where is the tail, and synchronize based on that. All that complexity is not implemented right now, and hence we are running into this challenge. So at this point, what I'm going to do is I am now going to go and debug this code. How many of you are using GDB? or have used GDB in the past? Have I put you all guys to sleep? Okay, so any of you are trying to do this along with me? Am I audible?
Yeah, you're audible.
Fine. So looks like I have lost most of the classes attention here. If I can have you guys back, it will help with the demo. Otherwise, the demo goes for a toss. It doesn't help anybody.
Participants are encouraged to respond to the questions. This virtual mode is
Yeah, really, we are not.
Yeah,
we are
yeah.
not getting the attention here.
Exactly.
So anybody tagging along with me?
And post-lunch sessions are normally very challenging.
Yeah, but Abhijat, that is why sort of we had decided to have demos here.
No. I mean, I actually mean that they are challenging for the teacher, the speaker.
Right.
Exactly.
I mean, as an audience, I can go to sleep, but as a speaker, I can't.
Guys, wake up. Come back to your desk. Yeah, let's go for
But I
the break
actually
in
like
that
this.
case.
Yeah, okay. Let's break and meet up.
Yeah, and post break, we will meet with the actual demos, including the bakery algorithms.